Let me start by thanking the organizers for extending this invitation and giving me this opportunity to give this talk here. So I'll be talking mainly about gravitational waves, and I was planning to talk about memory signals and the Soft-Graviton theorems, but for this audience, I thought it would be more interesting to add fuzzy dark matter, that how do you probe fuzzy dark matter using gravitational waves. Some work which we have done, so I thought that. So I'll have a small discussion about this fuzzy dark matter. Okay, so gravitational waves are actually, not discovered at LIGO. They were discovered at this Stellar binary pulsar. So this was in the 70s. They discovered that when you have a binaries orbiting around each other, then there is a loss in the time period of these binaries. And after many years of observation, so here they could track the orbit, so they could tell the masses and the distances and the eccentricities of this orbit. And from that, they inferred that there is a loss in the time period. So it takes shorter and shorter time to return to the same place for the pulsars. And that they have then attributed to this emission of gravitational waves. So these pulsars, they are slowly radiating gravitational waves. So these pulsars are at a distance of 1 AU, the Earth-Sun distance, and the time period is of the order of 8 hours. So they go around in 8 hours, and this 8 hours converts to something like 10 to the minus 19 electron volts, which coincidentally is also the range of mass range for the fuzzy dark matter, which is why fuzzy dark matter will come in, be important for this. Okay. So this energy loss by the pulsars was calculated by Peters and Matthews long time back using the Einstein quadrupole formula, and they gave a precise analytical formula for this elliptical orbits. So you can then check this dE by dt then decides what's the rate of change of the time period. So you can compare with experiment and see that if that matches. And from 74 onwards, they observed this Stellar binary, and it matches the prediction of GR, that particular formula, to 1%. Because the 1% uncertainty is actually the uncertainty in determining the masses and the orbital parameters. So GR is good to 1%. And if you have new physics, that's less than 1% of GR. So if you have something else going on, that should perturb this system to less than 1% of what GR is doing. Okay. The recent gravitational wave, which everybody knows, is you have a signal which is observed at Hanford, these two detectors of LIGO, and now there are many more detectors, and there is an offset of few nanoseconds, which you account for the time that gravitational wave moves from one detector to the other, depending upon the orientation of the source. And if you account for the offset in time, the two signals will match exactly. So the characteristic of this signal is basically that you have increasing frequency. So they are getting narrower and narrower, and amplitude goes up. So that's what happens when the when there are two black holes, for instance, or two neutron stars, they're merging. So in the last stages of collapse, they go faster and faster, which is the same as this loss of time period, which I showed earlier. But this is happening at a much faster scale. Okay. And then they merge, and then there is a black hole form, and there is a ringing of the black hole. So the interesting part of the ringing is that there are characteristic frequencies. So no matter how you perturb it, it will oscillate at fixed frequencies, and the damping scale is also fixed. So the frequency, the ringing frequency, is a complex number, with the real part tells you what is the actual frequency, and the imaginary part tells you what is the damping time. So they are ringing black hole is like some sort of an atom in which there are fixed energy levels. There's some sort of quantum object here. But I don't think one has shown that this ringing part is actually matches observations, because there are, I mean, it is consistent with the ringing of the black holes, but it could also fit ringing of other exotic objects which are merging, which are not black holes, for instance, wormholes, things like that. That's now this is actually the future, but this data actually for for pinning down new physics, for instance, fuzzy dark matter, this actually is less useful than the precision observation of binary pulsars. Now there are many more observations of binary pulsars and a white dwarf and a pulsar and two white dwarfs and so on. And you have the precision observations, and the advantage there is that from the time period measurements and from the orbit measurements, you know the masses and all the other details of the orbit, and then you predict the signal. Whereas here, this is all you have, and from here you fit in the masses and the spins of the black holes. So you don't have any more independent observations apart from the signal itself. So the traditional way of calculating this energy radiated is the third derivative of the quadrupole distribution of the source, and this t is time, the third time derivative of the quadrupole moment, a square of that. So this was established by Einstein in 1918. So that was the high point of his contribution to this. Because after that, he had doubts about whether these gravitational waves are real or not, because he always went back to his equivalence principle that you can always find a frame where you can make gravity disappear. So you can go to the elevator frame where you can disappear the gravity of the Earth. So he always thought that maybe this is a frame thing. I mean, it's a gauge dependent quantity that it depends upon your frame. It's not a frame independent thing, these gravitational waves. So it was, I think, in the 60s, with Pirani and others, they showed that basically these gravitational waves are changes in the Riemann tensor, and the Riemann tensor doesn't, you cannot, it's the second derivative of the metric, so that doesn't go away. You cannot remove the Riemann tensor by going to a preferred frame. So that is real in that sense. So in any case, now people believe, of course, that gravitational waves are real, but this is a formula still used, and of course corrections to that, Newtonian corrections, the post-Newtonian corrections to that is the one which is used by the experts for calculating gravitational waves, the classical GR formula. So here in this talk, I'll be telling that I'll be discussing a way in which we use this language of field theory to do this calculation of gravitational waves on binary orbit, use Feynman diagram language. So far we have only done tree-level diagrams, in the sense that there are no loops. So we get, and we have checked with the classical results, and we say that the tree-level diagrams give you the same result as your classical GR formulas. So that is the example I'll show you. But here, this could be a way in which you could then start probing. So for instance, this is the coalescing binary, that is the source, and this emits a graviton, and that graviton is seen in the detector over here. So this is just a single vertex Feynman diagram. So if you calculate this in the language of Feynman diagram and treat this source as a classical current emitting a graviton, then you can check whether this matches your Peters-Matthews formula, for instance, or not. So just a quick summary of what you do in the linearized gravity calculations. You start with this Einstein-Hilbert action, expand the metric around some background. So here we take this Minkowski background with the parameter kappa, and this kappa is this 32 pi g, the Newton's constant. So it's basically 1 upon m Planck. So to this action, you add the action of the matter written in a covariant way. So that also involves the metric. And then you expand the metric in both places, okay, to this linear order in kappa. So that's the linearized gravity. So what you will get at the Einstein-Hilbert part is basically the kinetic term for h mu nu. So it will be h mu nu box h mu nu. And here, when you expand this, you will get the interaction of matter with this h mu nu, if you keep the terms first order in h mu nu. I should speed up. So to calculate a action to first order in this thing, you use the Taylor expansion, take the derivative of the metric of the action, and then delta this quantity, kappa, this is delta G mu. So the derivative of the action is T mu nu, and this extra perturbation is kappa G mu nu. So that tells you that the coupling of matter with gravitons is basically of the form kappa T mu nu H mu nu. And this is universal, where T mu nu is this stress tensor of the matter action. So this is a universal coupling. So this doesn't matter what form of matter it is, it always has to be the T mu nu which couples to the H mu nu. And I'll skip this because, okay. So basically the gauge, there is a general covariant symmetry is this one that you can change X mu to X mu plus any function of X mu. Then the metric H mu nu changes as a tensor, so that changes like that. And if you take this current, interaction and put in this extra terms, then you'll see that if you integrate by parts, okay, this del mu operates on T mu nu. And if you hold this condition, the conservation of stress tensor, okay, now this is a partial derivative, these are not covariant derivatives. So this is the condition where the current is conserved and this vertex is invariant under this gauge transformation. So this is like your word identity in QED. So this kind of thing is useful when you are doing the calculations for Feynman diagrams. Okay. So basically what you do for energy loss, you take a vertex, E mu nu, epsilon mu nu, okay, and then you square it. So you treat this graviton as a quantum object and T mu nu as a classical object. I mean, this is the classical current. So square of this is the probability and this thing amplitude square of emitting the graviton, and then you multiply it by the phase space factor. So this is the Fermi golden rule, which tells you what is the probability of a quantum process taking place. So we use this formula. And for the T mu nu, for the, let's say we have a binary, we use this mu times u mu u nu. This is just the T mu nu of a classical point object. Okay. So we can treat it like a single object rotating around a center of mass with this single object having a mass m1 m. Yeah.
So here you're assuming this is, so this whole calculation is only for black holes, right? Because if
no, it works also. So it works if the wavelength of the gravitational wave is larger than the size of the object. So it will also work for neutron stars.
No, the formalism will obviously work. But I'm saying, suppose I take neutron stars, right?
Yeah.
Then I can't. Then I need to take into account the tidal deformation and things.
You could take into account tidal deformation. Yes.
Because then you can't treat it as a point object.
Yeah. So you have to have corrections to this form factors.
Yes.
In the T mu nu.
Okay.
Yes. That's correct.
Thanks.
So you take this Keplerian orbit, and the main this thing is this omega, the angular frequency. Okay, and this is what I said. This for the 8-hour period. This is something like 10 to the minus 19 eV. Okay. So we calculate the components of the stress tensor, and they turn out to be some Bessel functions. And since there is eccentricity, the angular speed changes during the orbit. So you have to expand it as harmonics of this fundamental angular frequency. So the angular frequency here is the expansion of many harmonics if it's eccentric orbit. With all that complications, this calculation finally yields this Peter-Matthew formula. So this is just a proof of principle that you can use a tree-level Feynman diagram type of calculation and get what you get from your classical. So this was done many years back, me and collaborator. And that time, of course, there was no use for other particles which can be emitted, but we still did the case of a scalar which is of 10 to the minus 19. So it's there in this paper. But now we have used this technology to find out what are the emission of other particles. So basically what we say is that if your black holes or the neutron stars are sourcing other fields like vector fields or scalar fields, and then they are going around, those other fields will be rotated, and there will be a loss in the time period, which you should see. So from the loss of time period of this, you can put constraints of the other light dark matter. So the scalar case was done by this. So basically for scalar and vector, it is the dipole moment, the change in the dipole moment. So this is the number of scalars, the number of the charge of the scalar divided by the mass, this ratio which comes in. And similarly, if you have ultralight vector bosons, this comes in here. Notice that this E dependence is different for these two. Okay. Did I make it? No. Sorry, omega no, there's some mistake, I think. I've copied the same formula. So there should be some difference. I think I copied. I will check again.
Subhendra, sorry, what are N1 and N2? I missed that.
N1 and N2, so this will be the total charge. Supposing you have a supposing you have some nucleon which couples to a phi. So you have psi bar psi phi. So it's the total number of nucleons.
So it's really numbers.
Yeah, number of the source.
Okay. Thanks.
So, yeah, the elementary source. So this for the sun, for instance, you will have 10 to the power 57 protons. So if the proton is a source, then N1 will be 10 to the 57.
Yeah, so it's the integral of the current, basically.
Yeah, of the charge, yes.
Yeah.
Yeah. No, it's not a gravitational coupling. It's a scalar coupling to the matter density, and also the vector coupling to the matter density. So these are separate couplings. So I'll show you one example where you have this fuzzy dark matter. So for instance,
can I ask one more question?
Yeah.
So you are just doing a tree level diagram, right?
Yeah.
And what about the corrections, higher order corrections?
So you see, it doesn't make sense to have corrections of the classical, the planets. You can't have loops, but you can have, of course, corrections of gravitons. So they actually, Ashok has done some calculation in which there are log corrections to that. But we have not done. So I should tell you about Ashok's calculations. There are, if you do corrections to that, you have log corrections. Also, you have log corrections in a different way. So I'll come to that. So you could have, like, for the tree level graviton correction. Yeah. So here, let's say we have I'll hurry up here. So let's say we have a vector boson, which is L mu minus L tau. So that is a current which is anomaly free in the standard model. So without adding fermions in the standard model, you can extend the gauge sector by this L mu minus L tau symmetry. And so if you have the extra Z, which is very light, so it is, let's say, ultra light, and it has a coupling to this current mu, then you will get this constraint from these observations from various pulsars and white dwarfs and pulsars. So notice that these fail at when this thing becomes heavier than 10 to the minus 17 or so, because the time period of that should be such that the frequency of those, the orbit has enough energy to excite these particles. Okay. Otherwise, you cannot produce these particles. So it's a coincidence that this is in the range of this ultralight dark matter. So this is sort of a probe of ultralight dark matter. So this we use the idea that neutron stars always have muons in them. So there is always a source of if this extra gauge sector exists, because neutron stars, in the neutron there is a decay to muon and anti-muon neutrino, and there is a equilibrium density of muons there. So this was also realized by Laha and his group. So they did the same thing, but they used the LIGO. So what their idea was that if you have extra radiation, then you'll have an extra contribution to the chirp signal. The chirp signal will go up faster, and then from LIGO you can put bounds on this. So, so this is some sort of a way you can probe ultralight dark matter. So here, of course, in Ranjan's case, it doesn't have to be ultralight, because now we are talking about black holes which are oscillating very fast, like the signal is not 8 hours, it's about like few seconds. So these will probe heavier dark matter, but we were, I mean, if you have only the neutron stars, etc., the binaries, then you will have this ultralight sector. Okay. So the fuzzy dark matter, just a little bit because it's not my main subject. So this was designed that you have this Compton wavelength, which is of the order of this kiloparsec, so that it doesn't fall into the center of the galaxy and create this cusp core problem. So to solve the distribution, what you do is you have a Schrodinger equation with this potential, where this potential is given by the Poisson equation. So there is you have to solve these two together. And when you solve these for the psi square psi, which is the current density, then you will get from that Schrodinger equation, you will get density perturbations in which you have this Jeans equation, where this is the gravitational attraction of the other. So this is the gravitational potential created by the dark matter. And here you get an extra pressure term. So basically this, what we call this quantum uncertainty principle, tells you that you cannot squeeze a particle beneath its lower than its Compton wavelength. So here, this is a quantitative version of that this actually gives you a speed of sound, the pressure term. Okay. So as we know that if this becomes larger than that, then there is a collapse. So this is the Jeans length for this particular thing, which depends upon the mass of the particle. So the Jeans mass, that is, if you take the Jeans length and multiply by the density, okay, and so you will get the Jeans mass. So rho times 4 pi by 3, the Jeans length cube. That is something like 10 to the 7 for a fuzzy dark matter of 10 to the minus 22. So basically, this tells you that what is the smallest mass galaxy you can form with fuzzy dark matter. So you cannot form dark matter galaxies smaller than this mass. So this yesterday, I mean, I brought this up because yesterday there was a talk about this probing the galaxy, the matter distribution in the galaxy. So I was wondering if people have done fuzzy bar dark matter in the galaxy, how it changes the NFW distribution to something else. Here it's an old result that the power spectrum at the megaparsec scales can, so it erases small scale powers as we expect. Okay, what is the, why is that number interesting, the 10 to the minus 22? It's interesting because it also coincides with the cosmological, what you need from this fuzzy dark matter to give you the correct relic density. So you have this potential, which is characteristic of your Number-Goldstone boson. There's a shift symmetry. And if you expand this in a power series, then the quadratic in A will be the mass term, so that you get the mass term from there. And you write the equation of motion for A, which is this. Then you say that oscillations, so you have the Hubble friction term, and then you have the oscillation term, okay, driven by the sign. You say that the time when this Hubble expansion rate is equal to the mass. So this, in the radiation era, the Hubble expansion rate is T square upon m Planck. So you equate T square upon m Planck to this small m, and take this small m to be 10 to the minus 22, you will get T equal to 500 eV. So basically at 500 eV, this will start oscillating, and this will behave like cold dark matter. Okay. And here you see that you get a F from this. Okay. And F is 10 to the 17 GeV for this mass of 10 to the minus 22 eV. So this is some in the ballpark of your gut string Planck scale. So that was made this interesting. So here we have a result that we have, this was pointed out by Hook and Huang, that if you have neutron stars in which the neutrons coupled to these axions, then, and if these same axions are also oscillating outside and providing you the dark matter, then should have a continuity between the two, inside the neutron stars and outside the neutron star, there should be a continuity. So basically the neutron star will act like as if it has a one long range force of these axions. And if they are light enough, then a oscillating neutron star with this axion force, with this axion current, charge will radiate axions, and you can put bounds on this. So this is what we probed, and So this effective charge has some corrections because of GR, which we provided. And then we said that the F here, the charge in the neutron star, this should have been 10 to the 17. But if it was that much charge, you will lose too much energy from the black holes and from the neutron stars, and that's ruled out from observations. So the F is actually smaller. Okay? So the uppermost F is this much from different observations. So it means that FDM, which coupled, so these particles, they do not couple to quarks or neutron star particles with this F. Okay. So next I'll quick word about gravitational memory. I'll take 2 minutes.
Can I just quickly ask a question?
Yeah.
Then you said, I mean, our classical axions, we expect them always to couple to strong matter, no? So in that sense,
Yeah, so your
classical axion story certainly does not
Yeah.
work. This is what I can conclude from this.
So if you have some axions which will ultimately couple to, which will solve your theta problem, then they have this relation M pi F pi
Yeah.
is MAFA.
Yeah.
But you have to break that relation. So these are not your classical
Exactly.
axions.
That's all I wanted to be
Yeah,
sure
these-
that I understood.
Yeah. So these are not classical. They don't obey that relation anymore. So this is what I call axion-like particles. Okay. So graviton memory is simply something that you saw this, there is a chirp signal. Now, if it has a DC component, that's called the memory. So basically, the oscillations of your arms of your LIGO detector, for instance, when there is a gravitational memory signal passing through, what will happen is in the end, they will not come back to the same place. So there will be a permanent distortion in space after the gravitational wave passes through. So in terms of signal, basically it means that there is a DC component in that oscillating signal. So there is some sort of a step function in there. And that comes out if in your calculation of the gravitational amplitude, or this is the amplitude in the frequency space, because that's what we calculate when we do Feynman diagrams. We calculate these in frequency space. If there is a pole, then the Fourier transform of the pole in the frequency space gives you a Heaviside step function, and that's your memory signal. So one should do a calculation in the frequency space of the gravitational waves, and then look for the poles. And that in the time domain will give you a memory signal. So that's what we did. So soft graviton amplitudes. So the idea basically is that if you have a scattering given by this of some hard particles, so in our case, it will be like 2 stars scattering each other or a star moving around each other, then the probability amplitude for emitting a soft gravitons, I mean the graviton energy is much smaller compared to the energy of these external legs, okay, will be a kinematical factor given by this in this bracket times the old amplitude. So the new amplitude for n+1 process will be an, the n process on the left hand side, multiplied by a kinematical amplitude. And the way it is derived is basically when you insert a new vertex in the external legs, okay, you put in the T mu nu of that current of this external leg, and you also create a external extra propagator. And this P plus Q whole square, 1 by P plus Q whole square minus this MA square, which is the propagator, will give you this P dot Q. And if you expand the T mu nu, you can expand it in powers of Q mu being the graviton frequency, and you can organize it in this way, in which you have just a linear momenta, then you have a momenta and the angular momenta, and then you have quadratic in angular momenta. So this is just the expansion of the T mu nu. And all of them have this P dot Q, which comes from the propagator. So basically here you have this propagator term in the graviton signal in the frequency space. And I said this and there is a pole in the propagator. And as I said, if there is a pole in the propagator, then you will have a memory signal. So that is the connection between the soft graviton amplitude to the memory signal. So you can actually use some sort of a soft graviton amplitudes to predict your memory signal. I'll give you an example of this. So we did a calculation of this memory signal for binary orbits where you have a hyperbolic orbit. So in that case, you have a memory signal. You do not have a memory signal in the linear regime for this elliptical orbits. You have to have states which are asymptotically different. 2 particles come in and they go out. that's what creates a memory signal, that asymptotically space becomes different in the past and the future. So we have a binary orbit and we calculate the T mu nu. Now instead of Bessel's functions, you have these Hankel functions. And we do this, so this was done by Arpan Haidt, who's sitting here, and Suraj Prakash. And then we take that signal and we take the zero frequency limit of these functions. So what we notice is that we get a 1 by omega term and we get these log terms. Okay. And then we look at calculations of this Ashok Sen and Sahu, who said that in their calculations, they have this 1 by omega terms and then they have these log terms. Okay. And when we took this formula and we took this for the two particle scattering, we converted this PA, PV, the initial momenta and final momenta, into the orbital parameters. And we saw that that matches this exactly. So this was a nice verification that what you can get from your soft theorems can actually give you something which is a practical result. So this, you don't have to go through this whole calculation. You can derive this, you could have derived this from the soft theorem. So this was a sort of a first demonstration that the log signals provided from this logarithmic terms can be obtained, match the one which are coming out from the exact calculations. So all this is in this paper which I was just mentioning. So that is all. You might all. Thank you.
Questions? Comments?
So if I understand correctly, with the scalar wave emission, you're imagining the operator in the Lagrangian is phi psi bar psi.
Yes.
Have you considered if you had the operator phi psi bar gamma 5 psi, so a pseudoscalar operator?
That won't work because pseudoscalar will couple to the spin. So you have to align all the spins to get a macroscopic.
Well, I was wondering, yeah, I thought about that, but then I thought you can also, when you do scalar production inside neutron stars from the psi bar gamma 5 operator, you can integrate over the spin structure function. So I was wondering if you could do it by integrating over the spin structure.
Yeah, so ultimately what you get, see, notice that I have a n1 minus the n square effect. But when you do that, you will get this thing proportional to n. You will not get, suppose you add the amplitudes and then square it. And what you are saying, just square each individual amplitude. The difference is a factor of n being the total charge. And that for neutron stars, etc., is 10 to the 57. So it makes a big difference in the numbers. So having a non-coherent emission doesn't give you a useful enough number.
But you might still get some small constraints.
Could be, yes. Yeah, in principle, yes, you're right. Yeah.
Okay, are there other questions, comments? Sorry. Oh.
So how is the strength of the gravitational wave? It depends on the mass of the axion. If I change them, because you took the mass to be 10 to the power minus 22. But if I increase the mass, because 10 to the power minus 22.
So there are two things. One is the amplitude, one is the frequency.
Yeah.
The frequency depends upon the mass.
Okay, the amplitude.
Yeah, actually the gravitational waves are being emitted by independent of this axions. The axions is the extra emission, which is changing the frequency. So the gravitational waves will not change because of the axions. That's the
okay. So it's the frequency.
Yeah.
So frequency will become higher.
Yeah. In his case, for instance, if you do, I'm doing only the Hull stellar, which is a slow rotation. But if you have mergers, then this extra energy which is being taken out will contribute to the chirp frequency. So then the chirp frequency of the gravitational wave changes.
Only the frequency.
Only the frequency. Yeah.
Are there other questions, comments? Anyways, if you have more questions, please write down in the Google Doc. We'll have a discussion session. If there are no more, let's thank the speaker again.
Thank you.